finish the coordination complexes, the crystal field theory and all that stuff. I hope you all had a chance to read and brush up your knowledge on the coordination complexes, because that will not be repeated here. We will be taking from wherever we left last time and move on with the bonding and coordination complexes, that reactivity of coordination complexes, and electronic properties of coordination complexes. So those are the topics for the Advanced Inorganic Chemistry course. And so next Tuesday, we will have uh, you all asked for a sample exam, right? So next Tuesday around the same time, I'll be uploading an exam. So you will be taking that exam during the class time. And the following Thursday, we will briefly go over any questions that you may have on the exam or any topics that require a little bit of refreshing. So I will do that following Thursday. And then the Monday after next Tuesday, we will have the actual exam administered around the same time, class time, and then continue from there with the other lectures. Are there any questions on this schedule? So next Tuesday, we will have sample exam, practice exam. Next Thursday, we will have a lecture to go over the exam. And the following Tuesday, we will have the exam one, the actual one that will count for your grade. The exam that you'll be taking next Tuesday will not be counting for your grade, although there will be some points there, but that will not come into the calculation of your total grade. That's only to give you an idea about how to handle problems. Okay. Are there any questions so far on that before we continue with the last couple of ideas in solid state chemistry and then move on to coordination complexes? Are we okay? Okay. All right. So somebody is asking me how similar. They will not be exactly identical, okay? Because from the topics that we've been doing, you can have multiple type of questions, but the sample exam or the practice exam only prepares you how to handle the concepts, but it will not be a duplicate of the actual exam. That defeats the whole purpose of giving a practice exam, okay? Yes, the topics will be similar, but the questions will not be same. Okay, having answered that question, let's move on to the uh, interesting aspects of solid state chemistry. Can you all see the board here, folks? Can you see the board when I can write it?
I can see
All
it.
right.
Yeah.
Yep. Very good. Okay. Uh, Unlike molecular solids, the ionic solids have an interesting aspect to the lattice energy. Remember, we talked about lattice energy in the last lecture, and we talked about Born-Haber cycle on how to estimate the lattice energies using a complex set of equations. Now, the reason why this is a big problem is, unlike in molecules, which are isolated stuff, in solids, we have a three-dimensional network of positively charged ions and negatively charged ions. Suppose if I take a one-dimensional network of, let's say, sodium chloride. Sodium is positive and chloride is negative. That is possible only if it is a molecule. But in a solid, I have another chloride on this side, and next to the chloride, I have another sodium. Next to the sodium, I have another chloride and sodium. And this whole thing repeats itself indefinitely and infinitely. I'm just showing only the one-dimensional aspect. Now, what we need to keep in mind is, when you have a sea of positive and negative charges, any given positive charge will not only experience attraction from the negative charge, it will also experience a repulsion because of a positive charge located at twice the distance of the anion. On the other hand, you also have an attractive potential from this positive ion and that negative ion, which is located about 3 times the distance. So if I call this d, that is the distance between the positive and the negative, then you have at a D, you have two attractive interactions, and at a distance of 2D, you have two repulsive interactions, and then at a distance of 3D, you still have an attractive interaction because of the chloride, although it is far off, but it will still have an attraction. So what happens as a result is, if you now look at the entire potential of the network, you can say if the charge is Z and Z, Z is the numerical value of the charge. If you are dealing with sodium, it is +1. If it is chloride, it is -1. So at a distance of D, we have two attractive interactions. That 2 tells you that you have an attractive interaction. And at a distance of 2D, we have two repulsive interactions, that is 2Z squared over 2D. At a distance of 3D, we do have, again, an attractive interaction. And at a distance of 4D, we have a repulsive interaction, and the whole thing continues. That is infinite. I'm just only showing one dimensions, but you can imagine the whole thing happening in 3 dimensions. So if I were to take a common factor of -2Z squared over D, and then look at the expression, this is simply 1 plus 1/2 minus 1/3 plus 1/4 minus 1/5, so on and so forth. Okay, so this series 1 plus half minus 1/3 plus 1/2 minus 1/5, anyone knows what that is? These are all series, right? Mathematical series. Any thoughts on what that expression leads to? Understanding chemistry requires a little bit of appreciation for math. Okay, with no knowledge of math, this whole thing looks very dry. The beauty of this is I'm having a series expression, 1 plus half minus 1/3 plus 1/4 minus 1/5 plus 1/6 minus 1/7, so on and so forth. If you look at the overall value, it is nothing but ln2. Natural log of 2. That's the value there. Okay. I found this on the web. Does it make sense to you? So in other words, this factor is good for a one-dimensional lattice. So whenever you are calculating lattice energies in a one-dimensional lattice, you need to have this correction figure ln2. This is called the Madelung constant. For a two-dimensional network, it's going to be different. A three-dimensional network is going to be very different. So people use the Madelung constants for different lattices to theoretically calculate the lattice energies, where there is no other information available, like Born-Haber cycle. If you don't have all the values, at least you can use Madelung constants and theoretically derive what the lattice energy is. The most important point here is that in a solid, you have both short-term and long-term interactions. So these are the short interactions. You also have potential felt by the ions in the neighborhood, next near neighbor, next near neighbor. So all these interactions come into the picture when you are looking at the lattice constants. So one way to avoid all these things, because of the complexity here, a Russian scientist by name Kapustinsky came up with a simple equation that will allow us to calculate the lattice energies of any imaginary ionic solid. He said the lattice energy, delta HL, should be equal to -n ZA times ZB divided by D times 1 minus 0.345 divided by D times a constant called K. That constant K is 1.21 megajoules per angstrom mole inverse. These are the units. So let's look at this equation. If you want to find the lattice energy of something like, let's say, calcium fluoride, very quickly, how do I do this? I can go back to this equation and plug in the relevant factors. So let's understand this equation here. This N here refers to the total number of ions in the formula. That's very important. So how many ions we have in the calcium fluoride? We have 1 calcium and 2 fluoride. So a net of 3 ions. So N value for calcium fluoride is going to be 3. For a sodium chloride, it will be 2. What will be the N value for a calcium sulfate?
Five.
No, we're looking at ions, right? Not the atoms. So in calcium sulfate, we have 1 calcium cation and 1 sulfate anion. So the N value is 2 here. That's the reason why I brought this example. Sometimes people quickly calculate the number of atoms, but that's not what we're dealing with here. We're dealing with the interaction between ions. Am I clear here, folks? So once you know that, then ZA and ZB refer to the charges on the cation and charges on the anion. For example, in a calcium fluoride, calcium is 2 plus and fluorine is 1 minus. So you don't have to put 1 minus there because there's a negative charge here. So you can just put a 1 value there, plus 1 there. So I do have the charges. And finally, the D is the distance between the ions, which we can say radius of the cation plus radius of the anion. So in this example of calcium fluoride, we can say that will be the radius of calcium 2 plus radius of the fluoride anion. Am I making sense here, folks? So once these numbers are given to you, you just plug them right here and multiply this expression by 1.21 megajoules. Understand this is not kilojoules and megajoules. So you can calculate the numbers very quickly. So this is the beauty of Kapustensky's equation, which allows you to calculate the lattice energies, not exactly, not very accurately, but very close. At least you will have some idea about, let's say if I have a solid like lanthanum fluoride, LaF3, I don't have all the information about, the heat of formations, electron affinities and all that stuff. If I want to know what the lattice energy is to be, I just go to this equation, LaF3. What should be the N value here? We have 1 lanthanum and 3 fluorides. So the N value should be 4 in that case. And then charge of lanthanum is 3 plus, charge of fluoride is 1. And once the radius of the lanthanum and fluorines are given, you should be able to calculate the lattice energy without any issue. Am I clear here, folks? Any questions on this? So the practice exam, of course, I will give you a problem using this equation. Again, you don't have to memorize this equation, but it's always good to keep that next to your notes. So if there is a problem on this, you can quickly refer to this equation and be able to calculate that stuff. Any questions before we continue to the next topic? Anything that's not clear? That's about what I would like to do in the solid state chemistry. Not that this is all there to know about solid state chemistry. In fact, what we did was just tip of the iceberg. There is a much more to this interesting area, but this gives you an idea about how to deal with the solids, the structures, the arrangement of atoms, the close packing, and be able to calculate the radius of different atoms, densities. If you go back to our lectures, you'll see quite a lot of stuff on solids we have covered. In the interest of time and in the interest of the fact that there are other topics that also require attention, so we're going to move into what we call the coordination complexes and the bonding. So we'll start with so we all have heard about the complexes, naming of the complexes, isomerism of the coordination complexes, finding the charges, all that stuff we have done in the previous course in inorganic chemistry. And here, we'll try to understand what is the bonding. How exactly are the ligands bonded to the central metal ion? Okay. If you now look at the hexamine cobalt 3 complex here, we have cobalt in 3+ state, and we have 6 ammonia ligands. And these are all arranged in an octahedral fashion. So you have a cobalt, and you have the NH3 or the ligands arranged in all corners of the octahedra. Each line here is about what we call the chemical bond equivalent to 2 electrons. Right, okay. So the question then is, if 6 of the amine ligands, if they are all donating pair of electrons to the cobalt, or even if they are covalently sharing, putting 6 electrons on the cobalt 3+ will make cobalt 3-. That is impossible. You can't have cobalt, any metal in a compound with a negative charge. Have you ever seen a metal with a negative charge in a compound? You have anions that have negative charge, not the metals. Metals are always positive. So what is then happening here? How is this cobalt 3 holding on to ammonia? In other words, we are trying to understand the glue that binds the metal and the ligands. Okay. So clearly, simple electron donation is not going to work out. So we need to work on a different idea. So Linus Pauling, as you all know, one of the greatest scientists ever walked on this planet, came up with an idea that might explain a little bit about how the bonding happens. So what he said was, just like the hybridization that happens in simple molecules, he said, this one, if you have an octahedral geometry, the cobalt will use 2 of its d orbitals, 1 s and 3 p's. So you have a dsp3 type of hybridization, and that hybridization gives you the hybrid orbitals located along the octahedral directions, and the ligands will donate electrons to these hybrid orbitals. So Linus Pauling was able to describe the chemical bonding simply as hybridization. So you all know by now that complexes need not always be octahedral. Sometimes some complexes are tetrahedral, in which case Linus Pauling said we could use sp3 hybridization, just like you would describe the bonding in methane, right? And if you have a square planar complex, Linus Pauling said we could use hybridization of dsp2. Okay. So the question then was, okay, fine, this is good. We can simply apply the well-known valence bond theory, which is the hybridization theory, to explain the bonding in coordination complexes. And for many years, people thought it was good. But here is a fundamental problem with this approach. What's happening here is when you use the hybridization model, there are a couple of things that Linus Pauling could not explain. So even if you're a Nobel laureate, it doesn't mean that you know the solutions or answers to everything. Linus Pauling was very great in terms of chemical bonding for simple molecules. When it comes to coordination complexes, the simple hybridization theory fails for two reasons. Number one is most of the coordination complexes are colored. They have different colors. In other words, they have emission in the visible range. That is surprising. Unlike molecules, organic molecules, which are mostly colorless, the transition metal complexes usually have very intense color. For those of you who will be doing the advanced inorganic chemistry lab, you will be experiencing that firsthand. You will be making these complexes in the lab, and you yourself will see how the ligands, when they attach to the metal, suddenly give you brilliant colors. And you will fall in love with the coordination complexes once you look at the colors. That's so pretty. But this hybridization doesn't explain why the complexes should have color. In general, when you have color, it means there is some kind of a gap in which the electrons are getting excited and de-excited across. And in hybridization model, there is no scope for a gap. So that was one big issue. The second big issue was, let's say, if I look at two complexes of cobalt, one in which you have ammonia as a ligand. In the other complex, I have fluorine as a ligand. What is the oxidation state of cobalt in the next complex? The hexafluorocobalt complex. What's the charge?
+3. +3.
Plus 3 or minus 3?
+3.
Plus 3, you are absolutely correct. So what's the charge on cobalt in the hexamine cobalt complex? That's also plus 3. Now comes the thing. The colors are very different for these two complexes. Not only the colors are different, there is one more strikingly important observation that was made. That is, in the case of hexafluorocobalt, there were unpaired electrons. In fact, they found a total of 4 unpaired electrons in the hexafluorocobalt complex. When you go to the hexamine cobalt 3 plus complex, there were 0 unpaired electrons. How can we explain that by simple hybridization? Why is that this complex has no unpaired electrons? It has no magnetism, as you all know by now. Simple physics tells us if you have unpaired electrons or uncompensated spins, those charged particles, when they rotate, they produce a magnetic field. That's how the magnetization comes in some compounds that have unpaired electrons. You can never have magnetism in compounds that have completely paired electrons. Like water, for example, all the electrons are paired, and hence you have no magnetic property. Water is non-magnetic, right? But if you look at these two complexes, this was a strange thing here. Same metal, same charge, same electronic configuration, but very different outcome in terms of the magnetic properties. So how do people measure this? I'll just quickly spend a minute about the magnetism, because it's again a very important aspect of the coordination complexes. So I'll quickly tell you. Magnetism is measured by calculating what is called the magnetic susceptibility. A magnetic susceptibility is basically a ratio of the magnetization over the field that you apply onto the compound, magnetic field. When you calculate the magnetic susceptibility as a function of temperature, for all non-interacting spins, you see a graph like this. So this one can be fit into what is called a Curie-Weiss equation. Susceptibility and temperature are related in non-interacting spins by an equation called Curie-Weiss law, where C is the Curie constant and theta is the Weiss constant. For purely paramagnetic compounds, that means although you have unpaired electrons, but these unpaired electrons do not interact with each other, then the value of theta is going to be 0. That is when we say it's purely paramagnetic. Sometimes theta can be positive, sometimes theta can be negative. If it is positive, they say it's ferromagnetic. If it is negative, they call that antiferromagnetic. But in any case, using this equation, suppose if you inverse that equation, 1 over chi equals T over C minus theta over C. So if you were to plot 1 over chi versus T using this equation here, you get a straight line with a positive slope, and the slope here corresponds to inverse of the Curie constant. So once you know the slope, you can calculate the Curie constant value. And the effective magnetic moment is basically square root of 8 times C. So once you do this experiment, magnetic susceptibility versus temperature, once you get the graph, when you get the C value, you can calculate the effective magnetic moment. This is now related to the number of unpaired electrons by this equation. N here refers to number of unpaired electrons. If you have one unpaired electron, what should be the value of this? Square root of 1 times 1 plus 2 is square root of 3, right? So what is square root of 3? I don't have a calculator here. Something like 1.73? What do we get?
Yeah, 1.73.
1.73. 1.73, what we call Bohr magnetons. That is the unit that we use. Just like time is in seconds, length is in meters, amount is in moles. The magnetization of the effective magnetic moment is measured in Bohr magnetons. And a Bohr magneton by definition is E over 2 pi ME, MH. So you don't have to worry about that. The most important thing is calculate the 8 over C and see what the value is. If your value is 1.73, you know you have one unpaired electron. If it is 2.8, you know you have two unpaired electrons, so on and so forth. So by knowing the effective magnetic moment, you will see. On the other hand, if there are no unpaired electrons, the magnetic susceptibility as a function of temperature looks flat. Extremely small negative value, and it does not change with temperature. That is how you know how many unpaired electrons you have, whether the compound is magnetic or non-magnetic. Am I clear here, folks? Any questions on this? Just want you to appreciate how much of work went in to understand these complexes. People diligently measured the magnetic properties of all these complexes, found out how many unpaired electrons they have, and then tried to work out a model which can explain the presence or absence of unpaired electrons, as well as if you have unpaired electrons, you can calculate how many unpaired electrons you have experimentally. Okay? So with this background, we can clearly say valence bond theory is not adequate in explaining the bonding in coordination complexes. So we need to have something even more rugged, and that can explain why compounds are colored, why there is an optical gap in compounds, and also why some complexes have unpaired electrons and some don't have for the same metal. All right. So to explain that, people have come up with what they call crystal field theory. Oftentimes it is abbreviated as CFT. CFT is crystal field theory. All right, to understand the crystal field theory, we need to go back to our d orbitals, right? We all know metals, especially transition metals, have d orbitals, and there are 5 of them: dx squared minus y squared, z squared, dxy, dyz, dzx, right? So there are 5 unpaired electrons. So let's talk about a metal all by itself, purely with no ligands. So you have 1, 2, 3, 4, 5 orbitals. These are all of the same energy. If you have a simple ion in gas phase, if there are no ligands around it, all those d orbitals will have the same energy. That's what we call degenerate set of orbitals. Now, if I bring ligands around the metal, so I'm now bringing the ligands to make a bond between the metal and the ligand. As we all know, ligands have electrons. Remember the theory, we said all ligands are Lewis bases, right? So they have a pair of electrons that they can donate. So if they are coming from an infinite distance, like in a spherical model, what happens is you have the same d orbitals increase in energy a little bit. Why does it increase in energy? Because the d orbitals have electrons and the ligands also have electrons. So when you bring electrons from the ligand closer to the electrons in the metal, there is going to be a repulsive interaction. The electrons of the ligand repel the electrons of the metal in the d orbitals. As a result, it increases their energy. But still, it is degenerate because we have a spherical approach of the ligands. But when you actually make the compound, here is what happens. When you make the complex, you get the metal and the ligands in an octahedral field. Is that correct? Here is the issue now. When you have a spherical orientation, you have an increase, but we still have the degeneracy. But once you have an octahedral configuration, then we got to see what happens to all these 5d orbitals. To understand that, we need to understand the orientation of the 5d orbitals. So if you have the metal here, that's your dx squared minus y squared, and this one is your dz squared. The dxy, dyz, dzx are in between the axes. So what is happening is the ligands here are coming and attacking the dx squared minus y squared and dz squared more preferentially than the xy, yz, or zx. This is almost like a head-on collision here. So the electrons of the ligand interact with the x squared minus y squared and z squared more than the other 3. So as a result, what happens is the set of 5 degenerate orbitals now break down to 3 down, 2 up. The up are the x squared minus y squared and the dz squared. So in other words, there is a splitting in the energies of the d orbitals. That's what I'm trying to say. And at the bottom we have dxy, dyz, dzx. Now this gap, that is the difference in the energies of x squared minus y squared and z squared, as opposed to the other three degenerate ones, is called the delta, or something is called crystal field stabilization energy, CFSE. This gap generally is in the optical range, and that explains why the complexes are colored. So when you excite electrons from the lower 3 to upper 2, you get a transition. The three triply degenerate orbitals are collectively known as T2G. Remember, in the point group classification, T means triple, right? So T2G means they're triply degenerate orbitals with a Garade symmetry. And the top two are E. E means doubly degenerate, again Garade. So there's a T2G EG splitting orbitals, right? So when you are now putting the metal electrons in the d orbitals, you need to be very careful. The other thing that you may be thinking about is, so we have some energy here. When we split, the total energy has to be conserved, right? You cannot create nor destroy the energy that is there. So when you're lowering 3 orbitals and increasing the energy, that lowering of energy must be exactly equal to the increase in the energy for the 2 orbitals. So we can say that the 2 times 3/5 delta 0 must be equal to -3 2/5 delta 0. So this is for the EG orbitals, that is for the T2G. Again, to understand this equation, again, we look at this. There are 2 EG orbitals. There is an increase in energy for them. That increase is 3/5 of delta 0. Delta 0 is the total splitting energy here. And then 3 of them are lowered. So each one is lowered by 2/5 of delta, so that if you look at the equation now, they are just identical. So we have 6/5 and 6/5. So that's exactly the energy separation. So if I know the delta Z0 value, how do I do this? You can do simple visible absorption spectroscopy and see what wavelength of light is absorbed. Once you know the wavelength of the light absorbed, lambda, then you can calculate the energy, which is hc over lambda. So once you know the wavelength, you can calculate the energies. Once you know the energy, that's your delta, from which you can calculate using this equation, what is the actual energy of the x squared minus y squared, actual energy of the dz squared. One of the interesting aspects is this splitting energy, or the crystal field stabilization energy, depends sensitively on the nature and identity of the ligand. Different ligands produce different splittings. Some produce strong splitting, they're called strong field ligands, and some ligands produce very weak splitting, they are called weak field ligands. So you can classify ligands based on their ability to create a splitting between the T2G and the EG orbitals. Okay, so let's try to see how this scheme now allows us to calculate the unpaired electrons and the location of the unpaired electrons in the coordination complexes. But before I continue, are there any questions so far?
I have a question.
Yes.
Is the splitting of the energy same for all the metals?
No, we'll get into that aspect.
Okay.
Different metals have different splittings. Okay. The splitting energy depends on the valence state of the metal. larger the valence, higher is the splitting energy. And as you go down the periodic table, for example, if you go from manganese down, right? So elements down below, like rhenium, have a larger splitting compared to elements above. So we'll get into that in a minute. And the nature of the ligands also has a role to play with this. So let's look at a few complexes and then see how we can estimate the electronic configurations of the coordination complexes. So moving on. Let's say I have a complex TiH2O6 3 plus. Okay. So how many unpaired electrons this Ti3 plus has? How many unpaired electrons? What? Titanium 3 plus. Sorry, I don't know why you guys are not talking. I don't care, it's okay. If you want to remain silent, that's your right. But an active learning happens when there is a dialogue. You know that very well. So I appreciate if somebody can, we don't have to come up with the right answer. We started this lecture with Linus Pauling, right? A Nobel laureate who was wrong. That's possible. Even a great scientist, no, we sometimes make mistakes, but we learn from our mistakes. Okay, so you don't have to feel bad about these things. All right, titanium 3 plus is argon 3d1. So there's one unpaired electron in this. So again, when you look at the crystal field splitting, right, we have 2 up, 3 down. So if you have only one unpaired electron, that unpaired electron goes into the T2G level. That's where it gets stabilized. Electrons are stabilized when they occupy orbitals of lower energy. So this is the configuration. So we say the electronic configuration of hexa aqua titanium 3 complex is T2G1, because that single electron is now in the T2G level. Am I making sense here? Right. So let's look at another complex. Let's change this complex to manganese 4 plus. Hexa aqua manganese 4. Water is a neutral ligand, so charge of manganese is 4 plus. What should be the electronic configuration of manganese 4 plus?
Argon D2.
Can you check one more time, please?
Uh,
3D1.
No. Manganese 4 plus. The neutral manganese is argon 3D3 4s2, right?
oh yeah.
3D5 4s2. Okay, that's the neutral manganese. If I'm removing 4 electrons, 2 of these will be gone, and the remaining 2 come from the 5. So what will be the remaining one now? We have 3 electrons remaining. So that's the argon 3D3. This is a common material, right? Manganese 4 plus has an electronic configuration of argon 3D3. So where would the electrons be there now in this crystal field splitting? Those 3 electrons will occupy 3 different states there. So the electronic configuration will be T2G3. Am I making sense here, folks? Suppose if I ask you, what is the effective magnetic moment of this complex? That will be square root of n times n plus 2. That is the number of unpaired electrons. In this case, we have 3 of them, 3 times 3 plus 2. What is 3 times 3 plus 2 square root of it? Can anyone quickly tell me? There's
3.87.
Huh?
3.87.
3.87, you're absolutely correct. Sometimes the questions will be, they'll give a complex and ask you what's the effective magnetic moment of the complex. So you go, write down the electronic configuration, look at your T2G configurations, and then be able to do this. Am I making sense here, folks? Questions up to this point?
I have a question.
Sure.
The square root of 3 times, like that equation, the n plus n2, that, what did you say you would ask us? Like, what is that looking for again?
Effective magnetic moment.
Okay, thank you.
Sure. Sometimes if you give the effective magnetic moment, you should be able to calculate the number of unpaired electrons too,
Okay.
right? You should be able to do both ways. Okay, great. So let me give you a couple more examples and then get into some interesting stuff here. We're not done yet, we're just starting. Let's say if I have hexaqua copper 2+ complex. So that is copper and 2+. What should be the electronic configuration of copper 2+, folks? It's argon.
I'm gonna say D9.
You're absolutely correct, sir. Got D9. So now if you want to put the electrons in T2G and EG, how would you do this? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? How many unpaired electrons do you have in the copper complex now?
1.
Only 1. So the electronic configuration of copper 2+ in this complex is T2G6, EG3. So that tells you there are a total of 9 electrons, 6 of which are in the lower level because T2G is more stable than EG. So what is going on here? I'm making sense here. Let's do one more. Come back to the manganese, make it more interesting here. Plus. We looked at the previous example, manganese 4+, right? When we come to manganese 3+, things are going to get a little messy. And we will see why that is the case. So before we do that, what's the electronic configuration of manganese 3+? It should be argon 3, 4, right? Agree with me?
Yes.
Great. So now I have T2G and EG levels. I need to place a total of 4 electrons into this grid. So I'll start with the lowest one. 1, 2, 3. There are 2 possibilities for the 4th electron. The 4th electron can stay here, or it can go here. So 2 possibilities. Now, to understand these 2 possibilities, we need to quickly look at what factors might lead to which type of electronic configuration. if this gap delta is large, what would be your choice, whether the electron goes there or comes here? If the splitting energy is huge, then it takes a lot of energy to keep that electron there. Instead, this electron will come back here and pair it. In which case I will have two unpaired electrons. On the other hand, if the splitting is small, then the extra electron will come here. So the electronic configurations for delta large and delta small are as follows. For the large splitting, it will be T2G4 EZ0. For the small splitting, we have T2G3 EG1. What is the difference between them? This has 4 unpaired electrons. This has only 2 unpaired electrons. So if you calculate the magnetic susceptibility, it will tell you what the delta might be. You can also do, of course, optical absorption spectroscopy to know exactly what the splitting is, whether it's large or small. A large splitting means the wavelength will be smaller. On the other hand, if you have a small splitting, the wavelength will be larger. So by looking at the wavelength of absorption, you should be able to qualitatively say which one is a large splitter, which one is a small splitter. So here are the choices. When you put the electron in the lower level for the manganese 4+, for example, in this one, T2G4, you have electron-electron repulsions. On the other hand, when you put the electron in the EG, you need to supply a lot of energy. So Mother Nature always chooses which one is energy, follows energy economy. Mother Nature never makes a mistake, right? It always wants to give you the most energetically stable configuration. So that is what this manganese 4+ is now giving us. So what people have found is this splitting, whether it is large or small, depends on the ligand. Some ligands produce very large splitting. They're called strong field ligands. And some produce very weak field. That means the splitting is not really huge. So just to give you an idea about the ligands, I'll write down what we call favoritely known as spectrochemical series. So you can go into the Google and find out spectrochemical series, but I'll just give you a small thing. Carbon monoxide of all the ligands is a very strong field ligand. So when you have carbon monoxide, it produces very high splitting. That followed by cyanides, followed by nitrates, followed by ethylene diamine, followed by ammonia. Up to this, these are all strong. And once you cross that, you have H2O greater than OH minus, greater than F minus, which is greater than Cl minus, greater than Br minus, greater than I minus. So for all the ligands, iodides are the weakest ligands. So when you have an iodo complex, the splitting between the T2G and EG is the most weakest. That means the crystal field stabilization energy is very small. I'm saying the same thing in different ways, but you're getting the picture now, right? So when you have carbonyls or cyanides or nitrates or ethylene diamine or ammonia, generally nitrogen-containing ligands are strong splitters. On the other hand, water, hydroxyls, fluoride, chloride, bromide, there's nothing to do with the charge. It's all the energy levels that are dictated by the molecular orbital picture. Okay? And you will have access to this information. You can use this information in answering questions. The second thing that is generally the crystal field energy increases with the balance of the metal. So if I have manganese 2+ and manganese 6+, which one produces strong field or strong splitting?
The 2+.
2+, I said the stabilization energy or the crystal field energy increases with increasing valence.
Oh, okay. Yeah, then
That's
it's
the
gonna
reason
be
why I put that arrows there. It goes proportional to the valence state. So higher the valence, more the crystal field stabilization energy. Am I clear? Similarly, 4D, 5D metals produce greater splitting compared to 3D metals. So it generally, in the periodic table, as you go down the group, the stabilization energy increases. So if I have platinum 4+ rather than iridium 3+, rather than palladium 4+, ruthenium 3+, moly 3+, manganese 4+, manganese 2+. So if you have any 3D or 4D metals, I have not given you an exclusive list of all the elements. You can look at the periodic table. For example, I'm not talking about osmium here. I'm not talking about rhenium there. So whenever you're dealing with these metals, you can close your eyes and say the delta is huge. It does not matter whether you have a weak field ligand or a strong field ligand. When the metal is a 5D or 4D, invariably that is going to give you a strong splitting. Am I making sense here? Questions up to this point? So let's take a few more examples of this. Let's say how many unpaired electrons this complex will have? How do we do this? Sometimes we'll ask, what's the effective magnetic moment of this complex? First thing to do is, what is the oxidation state of iron here?
Is it +2?
That is +2. What is the electronic configuration of iron +2? Argon?
3d6.
3d6. All right. Now, this d orbitals will split into two sets of T2G and EG. What do you think the delta is, large or small here? What's the ligand here we're dealing with?
Strong field ligand.
CN is a strong field ligand.
Yes.
This energy is huge here. The separation between EG and T2G is really large. So when the separation is large, you usually end up having low spin complexes. That means the number of unpaired electrons will be small. So let's write down those 6 electrons here. 1, 2, 3, You have the choice of putting the electron here or here. Where would the electron go?
Down. Like on the
Bottom.
Down, because this is a uphill battle here. That energy is extremely huge. So down, down, down.
So it's a diamagnetic.
This is diamagnetic. There are no unpaired electrons here. Am I making sense here, folks? What if I change this to three minus? All right. So now, if you look at this, is it diamagnetic or paramagnetic?
para.
So again, you write down the electronic configurations, T2G and EG. You have 5 electrons, 1, 2, 3. The fourth electron cannot go here because it's a cyanide. So it will come back here. And that is 4 or 5. So the electronic configuration is T2G5, EZ0. No electrons in the top 2. One unpaired electron. The effective magnetic moment of this is going to be 1.73 Bohr magnetons. So you see a simple change in the complex now gives you 2 different things. The ferrocyanide is diamagnetic, but ferricyanide is paramagnetic. Am I making sense? I also will tell you, one of them kills you, the other one doesn't. You know which one?
The diamagnetic one kills you.
Huh?
The diamagnetic one kills you.
Stay with that answer. We will give you a more rational approach. You might think that the diamagnetic one kills you, but in reality, the diamagnetic one is the most innocuous one. It's like water. But the other one is a toxin. It kills in a few minutes. Ferro and ferricyanides. And all that is tied to these things. We will talk about that as we go through this bonding and all that stuff. I'm just introducing the theory, right? We look at the activity of these complexes based on the electronic configurations. Then you will know why one kills and the one is absolutely innocuous. All right, are there any questions up to this point, folks? Anything that's not clear? So now you know the splitting, you know what kind of ligand effects, you know the metal effects, you know the valence. Higher the valence, the larger is the splitting. And you also know how to calculate the energies now of each of these orbitals. So we have covered quite a lot of ground here. Are there any questions before we move on to the next topic? Now, the next thing is, what happens in tetrahedral complex then? We've been talking all the way to octahedral complexes. So what happens in tetrahedral complex? So here is what happens in tetrahedral complex. So in tetrahedral complex, we have, let's say, PbI4 2 minus. It's a tetrahedral complex. 4 ligands in the metal. The way we look at it is, we look at a cube where you have the metal here in the center, in the body central position, and your ligands are here, here, and here, and there. Opposite corners, right? The 4 ligands are there. Now, if you look at the d orbitals, the dz squared is along this direction. dx squared minus y squared is along this direction. The dxy and yz are in this direction. And if you see, the ligands are maybe closer to xy, yz, and zx. Not really head on, but somewhat closer. And they're completely away from x squared minus y squared and z squared. So as a result, what happens is, in all tetrahedral complexes, the splitting is just the opposite. The T2G is slightly higher energy and EG is lower. And because there is no strong interaction between the electrons of the ligands and the metal d orbitals, in all tetrahedral complexes, delta is small, which means you always get high spin complexes in tetrahedra. Not so with all octahedral complexes, but in all tetrahedral complexes, you get high spin. That means you get more unpaired electrons because the splitting is very small compared to octahedra. So the geometry, see how beautifully the arrangement of ligands around the metal influence the splitting. And that splitting in turn determines the number of unpaired electrons, the magnetic properties, and also the what we call the structural properties too. Questions up to this point? Okay, now we understand tetrahedral complexes. The splitting is just the opposite, and I gave you the reason why, because the orientation of the ligands and the relative orientation of the ligands to the orientation of the d orbitals is different in a tetrahedra, and that's what gives you a different splitting pattern. All right, so we will now move to the next topic and understand a little bit more of how interesting these coordination complexes are. Of course, every single topic we talk in this course is very, very exciting. It's very important fundamentally because coordination complexes, and we talked about that in the last semester, they're used in ligation therapies. They're used in a lot of medical values, and most of these complexes are used in catalysis. And, billions and billions of dollars of compounds are made using transition metal complexes. Much more than any other field you can think of. So these are all very, very important. So let's talk about we have copper hexachlocopper complex. Okay. So what should be the geometry of this complex?
Octahedral.
Should be octahedral, right? All waters in octahedral fashion. Good. But you know what? Most surprising thing is, whenever you have copper in octahedral coordination, your octahedra is never perfect. It is always distorted in one of two ways. Either you have a distortion of octahedra like that. Can you see this? It's compressed in the plane, expanded in the normal direction, or sometimes you can have a distortion like this. But what is for sure is you will never see a perfect octahedra. Not only in copper, there are so many complexes in which you don't see a perfect, symmetric octahedral complexes. In some of them you do, they're always perfect, some are imperfect. Why is that? So here is an important concept which leads us to Jahn-Teller distortion. Jahn and Teller, they looked at this problem of why some complexes are nearly ideal, why some are crooked. So to answer this question, here is how they formulated the problem. If you look at the copper is in 2+ state, which is argon 3d9. We already talked about this before. And then when you look at the splitting of the orbitals, you have T2G and EG, and you have T2G basically 6 and EG 3. Okay. Now, if you look at the thing, you have two choices here. You can have the dx squared minus y squared having a pair of electrons and the dz squared orbital having one electron, or you can also have dx squared minus y squared having a single electron and dz squared having a pair of electrons. That changes the game there. So in other words, you have a choice here of placing the single electron either in dz squared or dx squared minus y squared. What Jahn Teller said was, if the electronic configuration of a nonlinear molecule is degenerate, or that means you have a choice of putting the orbitals, the system will distort to remove the degeneracy. In other words, in all this, whenever you have a choice of having two electrons in one orbital, one in the other orbital, then you are talking about a choice. And nature will not give you the choice and splits this orbital in a way, one will be lower in energy, one will be higher in energy. That distribution of electrons in the orbitals will distort the geometry, because when you have an octahedra having electrons along the x square minus y square, that's that direction. If you have two electrons here, the ligands will be pushed apart, or if you have electrons in the z, that will be elongated along the z-axis. In either ways, you are going to have a distortion. So that distortion happens only if you have a choice. Copper is extremely famous example for Jahn Teller distortions. But not only copper, we'll also give a couple of more examples. Wherever you have a choice, the system distorts to remove the choice. So let me give you a couple of examples here. I'll just take on the, oh, I'm sorry. So we'll continue with that in the next lectures. Okay, it's already 3:15, cross 3:15. So we will see you next Thursday around the same time. We will continue with this, and we'll finish this lecture, and then we'll continue with the activity of the complex system. In the meantime, please review the material, go back slowly to all the examples. All right, thank you very much, and we'll see you next Thursday.